Okay, hi everybody. So when is a sequence bounded? Well, first let's just note that a sequence is a map from the natural numbers to the complex numbers, well, if it's a complex sequence. And the more typical notation in our book would be like to say it's z1, comma, z2, z3, and list them forever. And we could say like the z sub n. What we really mean is the z sub n where n is a natural number. It's like the input to this map. And instead of saying n maps to z of n, we write z sub n, just so that we don't have to write these parentheses. So anyway, that was just a note on notation. A sequence is a map, but it's easier to say the z sub n than to fiddle with some other notation. Okay. So before I give a precise definition, let me do part B. The counting numbers are unbounded. They go off bigger and bigger and bigger, and so they're not contained inside of any disk. The harmonic sequence, on the other hand, doesn't get bigger and bigger. First, I have to remember what it is. In other words, it's the sequence that x sub n, or I guess we're calling it z sub n, is 1 over n. In other words, as a map, it sends the natural number n to 1 over n, which is a complex number. It's also a real number, it's also a rational number. That, however, is bounded. These don't get bigger and bigger in absolute value. Their distance from the complex origin is contained inside some number. So I guess, okay, unbounded. The harmonic sequence, though, was bounded. Sometimes people say BDD for bounded, but I better not use too many abbreviations. Unbounded. The alternating harmonic, it will also be bounded. It'll sort of jump. It starts at 1, then it goes to negative a half, then a positive a third, then negative a fourth, and then positive a fifth, and then negative a sixth. So it's like 1 minus a half, 1/3, negative a fourth, 1/5. But just because it bounces back and forth from the left and the right, here we are in the complex plane, they're still all contained inside a ball, say of radius 2. A radius 2 ball would contain them. Even a radius 1 ball would contain them. Or maybe a radius 1.1 ball. So they are bounded. How about a constant sequence? It's bounded. What's a constant sequence? Like here's one. 3, 3, 3, 3 forever. X sub n is 3, or z sub n is 3. Or 3i. That's still constant. It's constant because it's a constant function. Any n is just mapped to 3i. And 3i is here. And so we can fit it in a ball of radius 4. So it's bounded. The sequence 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Here's 0, here's 1, 2, 3, so it goes 1, 2, 3. Z4, Z5, Z6, Z7, Z8, Z9. Z10 is there. Z11, Z12, Z13 is again 1. And so we can fit it in a ball of radius 4 or 5 or whatever. It is bounded. It fits in a ball. The prime numbers are unbounded. That's not obvious, but it is true. They get bigger and bigger and bigger. They do not fit in a ball. Do not fit in any single ball. Same with these ones. Okay. The digits of pi and base 10, they are, although we don't really know what they are, like we don't have a formula for the nth digit, We don't know a formula for the nth digit of pi, but they're bounded because digits are between 0 and 9. And that means that a ball of radius 10, it's a terrible ball, would contain them all. Okay, so there's the examples. Now we know. Okay, but precise definition, part A. There exists a capital B, that'll be the radius of our ball. Maybe I'll say R. Capital R, it's a positive real number. It could be a positive rational number if we wanted. So this symbol, I could write in words, there exists. Well, let me first do symbols and then I'll do words. For all n, we have Zn, absolute value, is less than capital R. This is the answer. This is a precise definition written in logical symbols. There exists a positive real number R such that for all natural numbers little n, the blank space here could be read, we have, or it's true that the size of z sub n, the size of z sub n is, it's a real number for sure, and is less than r. Okay. So in symbols, in words, and in pictures, what this means is we're thinking of the capital R is the radius of a ball, and here's the complex plane, and our sequence is somewhere, like Z1 is somewhere, Z2 is somewhere, Z3, Z4, and it's doing something. And if it goes off to infinity, it'll be unbounded. And what's infinity mean? I don't know, but it means that it doesn't fit in a ball. But if it doesn't fit in a ball, like, this ball doesn't contain it because here are some things that are outside of it. A bigger ball doesn't contain it because here are some things outside of it. Then it's unbounded. But if there exists some radius such that a ball with that radius completely contains all the z sub n less than r means all the z sub n are contained in a ball or disk of radius capital R. This is the concept. The word bounded should have this picture in mind. There's some radius, there exists some capital R, a positive number because it has to be the radius of a ball, such that for all the sequence, they're all contained in that one ball. All we need is to find one ball such that for all the n's, the sequence elements in size are less than that positive number. That means that they're in a disk. Okay. That's my answer. Quiz yourself. Go to a blank sheet of paper. And can you answer this? What were those symbols? Math, maybe. you don't have to write it in LaTeX, but that's in case you want to write it in LaTeX. But quiz yourself. When is a sequence bounded? You should be able to do that. And now, you want to understand it. In fact, you'll probably have to think of the picture first in order to come up with these logic symbols. So I think, when I see this question, what's the definition of bounded, I actually think of this picture. I have the z sub n's, and I want them all here so that I can find some capital R that is the radius of a ball that contains all the z sub n's. There exists a capital R such that for all the little n's, z sub n is less than capital R. And then this would be a little incomplete, because what's capital R? Well, if I tell you capital R is a real number, in fact, it's a positive real number. And what's little n? Well, I should tell you that what I mean is for n should be a natural number. 1, 2, 3, 4, 5, 6, 7, maybe 0. And then this is the modulus of a complex number, the size of a complex number, which is a real number, which is just the distance to the origin. Okay, quiz yourself.